Sure. Okay. No problem.
Have fun.
Goodbye, Christy.
Thanks, Christine.
Now we have about 28 people, so we can probably we can wait for a while, and then we can start in a few minutes.
Okay. All right. Sam, can I share my screen?
Yes. Yes.
Okay.
So holding now, I think we can start.
Yeah, can you start?
Mm-hmm.
All right. Okay. So hello, everyone. Welcome, and thank you for joining FLUXNET ECN annual workshop today. My name is Ho-Jin Lee, and one of the FLUXNET ECN workshop organizer. Before we start the workshop, let me introduce FLUXNET ECN and the annual workshop first. FLUXNET ECN is the Early Career Scientist Network, a community of about more than 400 members across 57 nations. ECN aims to connect early career scientists working within the FLUXNET community and the regional networks. For early career scientists, a supportive and accessible community that fosters collaboration is critical to ensure the future of the FLUXNET community. To address this, the ECN has focused immediate efforts to identify existing challenges and resources to build a stronger ECN learning community and enhance regional network representation and cross-communication, and establish a mentorship network for continuous engagement, particularly serving ECN members transitioning into study site PIs. And as you have already known, the ECN annual workshop will launch these efforts in a 3-day virtual event from today, July 31st to August 2nd, replicating its agenda across 3 regional time zones. So we will hear from speakers with individual topics for 3 days. For 2 hours of workshop, it will contain 2 or 3 presentations from invited speakers, followed by Q&A time. The workshop will also result in a community Q&A platform for mentor-mentee engagement in a Slack channel. During the workshop, all presentations will be recorded so that you can watch the videos again at the AmeriFlux YouTube channel later. After workshop, please share your ideas and opinions on the workshop by taking 5 minutes of your time. So it will be much helpful for us to plan future ECN workshops. Okay, so today I'm very honored to have 2 great scientists from Korea and China. Our first speaker is Dr. Minseok Kang. Dr. Minseok Kang is a senior researcher at the Korean National Center for AgroMeteorology and Kang, and lead scientist of the Korean Eddy-Covariance Flux Monitoring Network, CoFlux. He also serves Asia Flux and FLUXNET as a vice chair and community council member, respectively. He received his PhD in February 2013 from the Department of Atmospheric Sciences at Yonsei University, Korea. His advisor is Professor Jun Kim at Seoul National University. And he has tried to understand the interaction between the biosphere and the atmosphere based on eddy covariance flux measurements. He's working on operating the eddy covariance flux monitoring network, covering various agriculture and forest ecosystems in Korea with his colleagues. So he will share his experience in flux tower site design and instrumentation today. Dr. Minseok Kang, if you are ready, would you please start your presentation?
Yes. Well, thanks, Ojin, for introducing me. First, let me share my screen first. Okay, it works. Okay, thank you.
Yeah, we can see.
Okay, so hello, my name is Minseok Kang. I'm working at National Center for AgroMeteorology in Korea. I'm very happy to share my experience with you in the FLUXNET ECN online workshop. Today, I will give a talk about flux tower site design and instrumentation. This talk briefly covers flux tower structure, location and height, and mounting sensors, instruments, and safe equipment. The content covered this time can be found in the both books, eddy covariance and eddy covariance method. Both books contain very practical information related to eddy covariance, so they are highly useful. First, the flux tower structure. A tripartite tower, it can be folded and stored when not in use. It can be used in short vegetation, such as grassland or rice paddy. The biggest advantage is low price and portability. As I mentioned before, it can be used in short vegetation. Flux tower is considered as a building. Perhaps in various countries, including Korea, bigger flux towers are classified as buildings, and administrative procedures are involved in constructing a new flux tower. However, the tripartite tower requires little administrative works. Because of this advantage, it is widely used for a pilot measurement. Actually, before building a permanent flux tower in Cheonan, Korea, flux observation was started using a tentative flux tower based on a tripartite tower. The height of the flux permanent flux tower is 10 meters, which has a wide footprint to use the flux data by combining with MODIS output. Next, triangular climb-up towers. In other words, antenna-style towers. It looks like the form of a combination of three letters. It is often used as a meteorological towers, including AWS, automated weather station. It is a little more expensive than tripartite tower, but more stable. And it is not that bulky, so it is good in terms of flow distortion and canopy gaps, and stable for long-term flux monitoring. Typically, flux towers are constructed in the following orders. This is the actual construction of flux tower at the Cheonan rice paddy site. First, a hole is dug in the ground and concrete tower base is buried in the ground using a crane. Then move the tower to the tower base using a crane and connect it to the tower base, then fix the tower, and it doesn't shake using the guy wires. Then install a deck that can be accessed from the road to the tower. If you do not have a crane, it can be installed as follows. The tower base and the tower are connected by connect the wire between the car and the top of the tower. And move the car slightly to make a tower stand, then pick the tower. The mountain seen in the background of video is Mountain Meru. It was originally higher than Mount Kilimanjaro, but part of mountain was blown away due to volcanic eruption, resulting in its current height and shape. The next walk-up scaffolding style towers. It is much more comfortable to go up and down the tower using the stairs. However, since they are much bulkier than tripod or triangular climb-up towers, so more flow distortion and large canopy gap is inevitable. So, but it is the most durable of the three, so it is also suitable for long-term monitoring. For this reason, the NEON in the United States, the meteorological tower, including EDICO variants, is also a walk-up scaffolding style tower. There is also a hybrid style tower that combine the advantage of a triangular climb-up tower and a walk-up scaffolding style tower. There are stairs up to the canopy top, so you can walk up and rest of height higher than canopy top is the same as the climb-up towers. The price is reasonable and more comfortable than a triangular climb-up tower and less bulky than a walk-up scaffolding style towers. Next, the tower location selection. First, you need to decide if you want to place the tower on the national land or private land. National land, you need to convince the local government. And private land, you need to convince the landowner. In my experience, convincing local government is much more difficult. The basic assumption of EDICO variance is that the surface should be homogeneous and flat, but there is no site ideally satisfied this. So we need to find a more homogeneous and more flat site. And the larger patch size, the better. And in the case of remote site, such as the mountain, it is good if there is a road for good accessibility. In addition, it is good if there is infrastructure such as electricity or cellular networks for remote access. The final tower location should be determined based on the observed wind data from nearby weather stations. This is process of constructing the B-bone wetland site this year. First, we planned to construct a flux tower and visit the local government. The plan includes not only the observation component and observation period, but also the funding source and benefit for the local government. If the persuasion goes well, the local government will give you approval. Then visit the site to find the tower, appropriate tower location. At this time, smartphone GPS and map application and wind data observed nearby weather station are useful. Tower construction is completed and data is collected. Then drawing a footprint climatology map confirmed that the most of flux were measured in the wetlands area, the interest to us. Next, the tower height. Eddy covariance flux measurement must be made in the constant flux layer. Usually, the constant flux layer starts at 1.2 to 2 times the height of the canopy. Therefore, the measurement height must be higher than that. So not only canopy height, but also consider the zero plane displacement height. It means the height at which the wind speed would go to 0. And patch size is also an important factor. As the measurement height increases, the eddy covariance system measures larger areas. And it's not good when beyond the area of interest, as in this case. And let me introduce the relevant rule of thumb. For short canopy, the measurement height must be higher than 1.5 meter and lower than 1% of the patch. For tall canopy, the measurement height must be higher than 1.2 times the canopy height and less than 1% of the patch. This rule of thumb is slightly different for each researchers. But the important thing is that these criteria must be set the same when operating multiple sites. This increases comparability between the data. The measurement height is also linked with uncertainty in the data. The following time series are the time series of observed methane. flux at two different sites. The measurement height are different, 3.5 meter and 10 meter respectively. During the non-rice growing period, the methane flux is almost zero. As you can see, the observed methane flux fluctuation in the fallow season at a height of 3.5 meter are much smaller than oh, I'm sorry, my PowerPoint program is freezing now.
No worry. I think so far we can maybe ask people if they have any question. They can ask now, so we can wait for your computer to just recover. So now maybe if anybody has any questions so far, you can ask or you can post in the chat. So then we can wait for the program to just recover. Anyone? So you can post in the chat or you can just ask here. Oh, okay. If not, maybe I can just ask one. And so you just mentioned the height is about 3 times of the path. So I'm just a little bit confused about the path of the yeah. So maybe we can open the previous one, so I was just a little bit confusing about the path and the height of the flux tower. So maybe you can just clarify what. Oh, okay. So here at one question is could you also describe the zero plane displacement? So maybe one is about zero plane plane displacement a little bit. So yeah, so you can just explain a little bit about this. So now maybe I can also I can just put you as a host, so you can share your slides. So now I think you can share your slides because I just I made you as a co-host. Kang, I just made you as a co-host, so you can share your slides. I think it should be good.
Okay. Let me briefly explain
Okay.
what the zero plane displacement is. The wind because of the friction, surface friction, the wind speed close to zero at the boundary, the surface at the surface, but for example, in forest, there are many trees, so the trees makes friction. So the canopy height of canopy exactly the same, the height where the wind speed is 0. So zero plane displacement height is the height when the wind speed is close to 0. So
Okay, cool. So when so that you mean the wind speed, or it's the friction, wind velocity to friction, or it's the wind speed equals to 0.
okay, can we resume my presentation?
Okay, cool. Yes.
I'm sorry for this. So the fluctuation much smaller at 3.5 meter than at 10 meter. So this fluctuation directly related to the flux data uncertainty. So as the measurement height increase, a wider area can be observed, but the uncertainty of the data also increases. Okay, the observation area varies according to the measurement height, 10 meter and 5 meter. So this difference makes this difference leads to the difference in annual budget like this. So intercomparative observation should be performed when changing the measurement setup. In the case of forest, the canopy height may continue to increase. So the measurement height should be set considering this. When attaching instruments to the tower, new rail, crossover plate, or U-bolt are usually used. When installing sensors, leveling is very important. In the case of a radiometer and sonic anemometer, leveling directly affects data quality, so it should be checked periodically. And next, boom direction and length. Those should be determined to minimize flow distortion. So boom is the longer, the better, but less stable. The shorter, the more accessible. It means easy to maintain the sensors. Flow distortion is caused by the sensor and tower frames. So CSS3, the sonic anemometer, under measure wind speed when wind blows from behind the sensor. So, and if wind blows as follows, pointing the boom and sensor this direction, will reduce flow distortion. Since the walk-up scaffolding style tower is bulky, so you must use long and stable boom as shown in the pictures. In the case of spectrometer, data quality can be improved if a long boom is used. And connecting guide wire to the boom is good for stable measurement. I have experience comparing wind speed measurement on both towers, the permanent tower and mobile tower. It was confirmed that the relationship between the observed wind speeds at two heights varied with wind direction. Later, I confirmed that the reason was that other equivalent system blocked the wind. So please do not make the same mistake. The equivariant system consists of sonic anemometer and gas analyzers. Sonic anemometer is divided into directional type and omnidirectional type, right? Directional type and omnidirectional type. Appropriate correction must be applied according to model and manufacturing period. And gas analyzer divided into open pass, closed pass, and enclosed pass type. A closed pass analyzer has an internal sample cell. In sample cell means optical pass for analyzing the gas concentration. The sample cell is flushed by sampled air and open pass sensors. The sample cell is in the open air. An enclosed pass analyzer is a kind of closed pass analyzer. It looks like enclosing open pass analyzer. For one of our site, open pass gas analyzer LI 7500 was replaced with enclosed pass gas analyzer EC 155. CO2 and H2O fluxes were collected using both gas analyzer for several months. As you can see, there is a significant tube attenuation for the H2O measurement using enclosed pass gas analyzer. It should be I don't know why, but my
So now it's freezing again. No worry, no worry. We can
Freezing
wait.
again.
We can wait for a while. No problem. And we may also ask some questions. If now any has some question, you can post in the chat, or you can just ask here, so we can maybe have a little bit discussion.
Probably the presentation file has so many pictures, so it just continues to stop. Yeah.
So it's big
So
file, so
convenience.
it's very difficult.
If there is no question from the chat room, may I ask one question?
Yeah, sure.
So as you showed us, there can be a flow distortion according to the flux tower the design. So have you ever tried to compare the 3 types of structure and just explain how the people, the young scientists, researchers can identify the flow distortion from there?
That is very difficult. And
okay, maybe you can answer later in the Q&A platform in our Slack channel.
Okay, and
Professor Kang, so now there's one question is about advantage disadvantage between directional and omnidirectional anemometers. So maybe you can just answer this one before we just move on, so you can help to answer this question.
okay.
Disadvantage and advantages of the directional and omnidirectional anemometer.
So the disadvantage of directional type of sonic anemometer is there is I already explained this when the wind blow behind the sensors, the sonic anemometer under measure wind speed. So that is the disadvantage of directional type. And for the omnidirectional type sonic anemometer, it can measure the wind speed reliably for all direction, except this part. So okay, just a second. This supported frame. This frame also makes a flow distortion. So and okay, is it enough? Let's move on to the lightning load may help preventing. Oh yes, lightning load also makes some interrupt. Okay. So it should be noted that the H2O flux measured by enclosed path system was still underestimated after applying frequency response correction. And CO2 flux measured by open path system using open path system LI 7500 showed a significant bias due to the instrument surface heating during the winter. So it can be resolved by applying additional air density correction or change the instrument setting. It should be noted that spectroscopic correction error for other open path system, EC 150 and orgason. The error results from the use of low frequency temperature measurement in determining high frequency CO2 concentration. So using sonic anemometer, sonic temperature from sonic anemometer instead of thermistor for spectroscopic correction, we can resolve this issue. The flux data can be replaced using the empirical relationship between the spectroscopic error and sensible heat flux, like this. And the orgason is all-in-one eddy covariance instrument, that sonic anemometer combined with gas analyzer. However, a gas analyzer gas analyzing part, this part, is a little bit bulky, so it makes a flow distortion. A advantage, this advantage of closed path system is that inlet filter is often clogging. The EC 155 vortex filter has dramatically improved this problem. It reduces maintenance by supplying clean sample cell and sample gas to the analyzer sample cell. To install and maintain the eddy covariance instrument, you have to climb the tower. At this time, the necessary equipment is harness and ASAP rod. The harness is equipment that allows you to walk by hanging on the tower. It makes your hands free. ASAP and ASAP rod are safety equipment used when climbing up and down the tower. In the event of sharp road or sudden acceleration, the pole arrestor rocks on the rope and stop the user. This is the last slide, take-home message. First, know your site. Flux tower site design mostly depends on your site. For example, canopy height, patch size. Next, set your scientific goals. Flux tower site design and instrumentation can be modified according to your research purpose. And know your instruments. Each instrument has pros and cons. The appropriate correction should be applied for more accurate flux values. Safety first. Even if it is annoying, wear safety equipment and climb up the towers. This is the end of my talk. Thank you for your attention.
Thank you, Dr. Minseok Kang. So if there are questions from the audience, please leave at the chat room, or you can make any question after our workshop in the Slack channel. Okay, so Okay, our second speaker is Dr. Wang. Wang, are you there?
Yes, I'm online right now.
All right. So before we start Wang's presentation, I would like to introduce him to the audience. Dr. Wang received his bachelor's degree and master's degrees in electronic engineering from Tsinghua University and his doctorate degree from Princeton University in the United States. During his doctoral period, he focused on the development and application of new quantum cascade laser spectroscopy gas analysis technology. He founded HealthyPhoton, the company in China, in 2014, focusing on research and development of high sensitivity, high frequency trace gas analyzers for ecological and meteorological application scientific research. Today, he will talk about the latest instrumental research and applications for agriculture ammonia flux measurements. Okay, Dr. Wang, if you are ready, would you please start your presentation?
Yes, thank you very much. Could you hear me and watch my video?
Yeah, we can hear you.
Okay, great. Okay, so let's start. Hi, everyone. This is Wang from HealthyPhoton, a startup company. We are a startup company focusing on development of novel trace gas analyzers for ecology research community. Thank you very much for having me at FLUXNet ECN. To be honest, I'm not an ecologist. I'm an instrument developer, and this is the first time I give such a long presentation using English. So if you have any questions during the talk, please go ahead and interrupt me and ask. I'm happy to take any questions. So today's talk is about what we are doing in our company. We focus on one of the hardest gas to measure, which is ammonia. This is the outline of my talk. First of all, I will go through the background and motivation of this work. Ammonia emission is a big problem in China also. And then I will introducing the product. We give it a model, HT8700. I will describe the principle and advantages. And then lastly, the application cases and papers based on this kind of instrument. So let's begin. Let's start with social economy of mitigation of ammonia. In 2021, there's a science paper published by Zhejiang University and UKCH described the social economic value of abating ammonia pollution. Because ammonia in the atmosphere is an important precursor of PM 2.5, and the air pollution causes millions of premature deaths every year, resulting in huge social medical cost. So the world has been treating NOx and including nitric oxide and nitric dioxide, active nitrogen as an important source of industrial pollution and air pollutants for decades. However, ammonia as the only alkaline substance in the atmosphere has not paid enough attention. One of the main reasons is that ammonia itself, the high absorption and water solubility nature of such molecule make marrying ammonia much more difficult than other gases. For example, ammonia, 1 liter water will absorb 700 liter ammonia gas. So the research of this paper showed that the cost of reducing ammonia emissions is only 10% of the cost of reducing NOx. So that explains that the air pollution policy should pay more attention to the mitigation of ammonia emissions. So where's ammonia coming from? If you have done some work in reactive nitrogen area, I guess you've already known. Ammonia is a colorless gas with a pungent odor, some very soluble in water, strong absorption effect on any surface of the tubings, filters, cells, or containers that want to sampler this kind of gas. So this make trace level ammonia sampling and analysis very hard. In a paper published by Peking University, the team estimate that ammonia emission source contribute in China is mainly coming from agriculture activity. So the adds up of the total agriculture ammonia emission contribute over 70, even 80% of the total emissions, not like the NOx and SOx or ozones or CO, carbon monoxide. So this kind of gas or pollutant mainly coming from agriculture. Of course, there are a lot of scenarios or market needs. People want to reliable and accurate measure ammonia gases. For example, from industry emissions, they need point emissions, point emission concentration analyzer. For example, boiler flue gas, fertilizer plants that synthesize ammonia, and ammonia plants. Those are all from industry. For some agriculture, livestock farming, there are small closed farms, ponds, composting ponds, which need a point sensor. And for automobile exhaust, some diesel engine, you need SCR, which means selective catalyst reduction, as a reagent to reduce the NOx emissions. So in the engine or in the exhaust, there are some ammonia injection, but not all the ammonia react fully. So there are still some leakage of the ammonia reagent, which is called ammonia slip. So automobile exhaust also emit ammonia. Those are point sensors, but for large area emissions, we need flux measurement. Sources like large scale fertilization, farmland and grassland, large area livestock farming, and for some scientific community, people need ammonia flux sensors for atmospheric emission and dry deposition study and soil chemical study. So still, there are a lot of air flux sensors need for ammonia measurement. There are some current technology and products, including offline lab test chemical methods. As I said, due to the sticky nature of ammonia, there are large sampling error and labor cost for such kind of traditional methods. And these methods, since it's offline, so it's not continuously, so people actually need online analyzer to have real-time data. So there are some companies developing closed path trace analyzers for ammonia. Maybe you've been using some of this instrument, like ILGR, integrated cavity optical spectrometer, Picaro's cavity ring down spectrometer, and Booker's open path FTIR spectrometer. These machines are all facing challenges, like not portable, hard, large and heavy, only operatable in the lab. And since those are closed paths, they are facing slow response and high power consumption, because you need a very large pump, vacuum pump, to suck the air in. So the main focus of our work is to develop or explore the impact of agricultural fertilization on ammonia emission, deposition, flux, and different ecosystems. So the methodology we are using is to adopt eddy covariance technology based on a novel QCL-based open-pass trace ammonia analyzer. So this required there are some new requirements for this kind of technology. For example, people need high sensitivity and high speed for eddy covariance measurement. Your analyzer, gas analyzer, need measurement speed at least 10 Hertz. It also needs large dynamic range, which means before the fertilization, the ambient ammonia concentration is around 10 ppb or even lower. So your sensor need to measure 10 ppb level ammonia, but after fertilization, the concentration should shoot up to 100 ppb. So you need to have a very high resolution and large dynamic range for this kind of instrument. Also, it needs to avoid sampling error due to the ammonia adsorption nature. Sometimes the field station is far away from grid power, so you need to have this analyzer with low power. And in some East Asian area, there are some white raspberry. For safety issues, you have to make this analyzer powered by low voltage power supply. Those are all the requirements for the new scheme. So we decide to use mid-infrared spectrometer to detect such kind of molecule. So for this kind of mid-infrared spectrometer, one of the famous example is the James Webb Telescope launched to the space. There are several mid-infrared spectrometers instrument on the telescope payload. So scientists use a strong optical fingerprint to detect gas molecular components of the exoplanet X atmosphere light years away. So this is actually a remote and a non-invasive or non-contact measurement technique. Today, JWTS has found O2, SO2, CO2, water from the measurement, as I know. So this technology is based on the strong optical fingerprint of all this gas molecular in this 3 to 12 micrometer wavelength region. Of course, this technology can be used to detect ammonia as well. These are the wavelengths or the graph showing what we can measure from 3 micron to 14 micron, which is basically stand in mid-infrared or far infrared region. Ammonia is here, so you can see it's around 9 to 10 micrometers. Why we want to use ammonia, mid-infrared to detect ammonia, there are also some absorption peaks around near-infrared of ammonia, like let's say here. So here is a wave number of the near-infrared ammonia absorption, and here is the wave spectrum in the far infrared region. This is a wavelength. And you can see in the right block, the mid-infrared ammonia absorption is much stronger than those are in the near-infrared region. So with the high absorption or stronger signal, we can achieve trace level ammonia measurement. So we use a technique called tunable direct laser absorption spectroscopy, short for TDLAS. These lasers can be, this technology means a laser can be used for sensing gas phase molecular based on this kind of spectrometer. The sensor contains several main components a single wavelength laser, a wavelength covered absorption peak of the target molecular, a gas cell, which contains molecular, or we can, in our work, we choose as an open pass gas cell, and a photodetector to receive the laser intensity and transform into electrical signal. And of course, we have to use some electronics to drive the laser, to amplify the photodetector, to retrieve or to feed in the spectrum, to some algorithm to keep the analyzer stable, and to retrieve the signal and the concentration. So using modulation and lock-in demodulation, we call it as a wavelength modulation spectroscopy, we can retrieve the ammonia signal without any interference. And we also implement some algorithm in the analyzer to have the drift compensation. So this is a typical graph showing another TD-LAS analyzer, the result of a CO2 and water signal around 2000 nanometer. So there are some absorption of CO2 and water around this region. So by retrieving the signal of CO2 and water, you see there's a water, we basically retrieve the single line of the molecular or single transition of the molecular. So they are compared to the other wideband gas analyzers, this laser-based analyzer can avoid the interference between different moleculars. And to probe the ammonia spectrum in infrared region, we use a new semiconductor laser called quantum cascade laser. It's a new generation of mid-infrared laser source. So I'll give a brief intro about this semiconductor laser. It was invented by Bell Lab in 1994 as a new generation of mid-infrared laser source. QCLs were designed to contain thousands lasers of quantum molecules, electrons, movement in the conduction band, just like water in the cascade. So this is the reason why it's called quantum cascade laser. So the thickness and material structure of the quantum well determines the output wavelengths and the efficiency. So compared to the other mid-infrared laser sources, such as CO2 gas lasers, solid-state lasers, or OPO lasers, QCLs have advantages like efficiency, wavelength design flexibility, and small size. The semiconductor manufacture process for telecom laser chips can be used for QCLs without any problem. Therefore, once there is a volume market application, the unit cost can be quite low. The average price for QCL chip dropped by 3 to 4 times compared to that of 20 years ago when I had my college. So I think it's time for QCLs to bring us a new era of mid-infrared sensor or gas sensor applications. During my PhD, my major work is to develop novel gas spectrometers based on QCLs. I invented a sensitive and transportable nitric oxide isotope sensor for human exhaled gas analysis as a asthma biomarker. So basically, I developed a biogas sensor during my PhD thesis. And we brought it to Cleveland Clinic for in situ non-invasive asthma diagnostics. This is where I learned to build analyzer based on QCLs. When I started HealthyPhoton, I was told by our customer that there are needs for trace ammonia analyzer in ecological research community. So inspired by our Princeton colleagues' work, I developed myself I developed myself into the commercialization of QCL-based ammonia analyzers. It's the beginning of the open pass ammonia analyzer. So this is a configuration of the instrument. It contains a mounting post, the upper housing. So in the upper housing, there is a laser source, 2 detectors, one beam splitter split the laser beam into 2 different passes. One goes through the reference cell for laser line locking. So another goes into the open pass cell. Basically, this window, one window output the beam, shoot the beam into this multipass optical cell. The other window receive the beam coming from the optical cell, received by the sample detector. So there are upper mirror beneath this upper housing. There are lower mirrors facing upward. So we designed these optics mechanics to make this open Herod cell with about 50 meters measurement path. With such long measurement path, the analyzer can detect ammonia, ambient ammonia with a resolution around 0.3 ppb and 10 Hertz measurement speed. So this instrument is IP67 waterproof, and it can work at the operating temperature is around from minus 15 degrees to 45 degrees C. And we know that some area is pretty remote, and the manual cleaning of the mirror is very labor costly. So we develop a spider, shorts for spin dust emitted rotor, to automatically clean the lower mirror when the signal strength received by the photodetector below some threshold. So overall, the HT-A700 has 3 major advantages. First, it uses an open optical path design to avoid ammonia adsorption by the tubing and cell surfaces. So it can avoid high frequency attenuation or damping, especially for eddy covariance data analysis. Second, it avoids vacuum pump. So there's no need for power supply for such a high power. It's vacuum pump basically is power hungry. So without a vacuum pump, the overall system consumes only around 50 watts power when it's in normal operation range. So it's very easy or flexible for the scientists to select the deployment site. Third, it's extremely simple to set up. All you need to do is to hand the instrument up, connect the chiller and power up, and connect the communication cables. It starts working in half an hour. So this GIF shows the sensitivity and fast response of this analyzer. So we all know that human skin actually emits some ammonia due to sweat. And when the engineer put the hands around the open pass region, you can see the reading of the analyzer shoot up due to this emission of ammonia from the hands. And we also compare this analyzer with a commercial available CRDS analyzer in the room. So you can see in the y-axis, this ammonia concentration range is from 20 to 55 ppb. And during the 14-hour measurement time, the entire both of the instruments shows pretty similar trend of ammonia concentration change. We also compare this analyzer with another closed path spectrometer, which is manufactured by LGR. you can see both of the analyzer put in the room, put in the on the table inside a room, and this is one data just showed compared with Picaro's CRDS, and this is data shows the readings from HT and LGR analyzer, and we also did some high concentration ammonia released in the room, and you can see that the black one is a reading from HT analyzer, and the gray one is LGR analyzer. It shows a quick response of HT and up to 300 ppb and back to the ambient level. This work was in collaboration with Professor Zheng Junhua's group in IAP. So the first experiment of using this analyzer we've done is for vehicle-based ammonia mapping, and we put the analyzer on top of a SUV roof, and we integrate the system with a GPS, a combo data logger, lithium battery, and then we drive the vehicle around the farmland, and then we can see some fast response of the ammonia plume in a downwind direction, and the ammonia concentration map around the livestock farms can be retrieved based on the GPS value. So this experiment shows that this instrument, optical instrument, is pretty immune to the vibration during driving. And the second experiment is eddy covariance system deployment. We deploy this EC tower first in a Raspberry in the May of 2020, and the whole system include HT 8700 analyzer, a combos anemometer, light course 7500. We deploy the analyzer and Zhejiang Ningbo, and the overall system consume about 50 watts power and supported by 24 volts DC power, or this can be generated by solar panels. And this is the system performance. We estimate the detection sensitivity, and it's around 0.3 ppb and 10 hertz sampling rate. And for eddy covariance experts who are more care about the flux detection limit, we calculate this number, and it shows the system has a detection limit of around 7 microgram per square meter per hour. And this is the Allen deviation of this instrument, and shows when this and 10 hertz or 0.1 second sampling time, the concentration or resolution is around 0.3 ppb. And when you average the noise or you average the signal, you basically suppress the noise, or you smooth the signal out, and the noise can be even lower. And this is a cross covariance of the vertical wind speed and the ammonia concentration. Some samples, you can see the peak is pretty sharp, and shows the lag time. Since there's no tubing, the lag time is within plus minus 0.5 seconds due to this open path configuration. And we also did some testing before and after fertilizer application. We did experiment with application of ammonium bicarbonate on a rice paddy during the fallow season. So the system include the analyzer. We also include the light course 7500 to monitor the water flux, because you have to use WPL correction to correct the water dilution of the flux. And before the fertilization, you can see the flux is pretty close to zero. And just after the fertilization time, the instrument shows a peak of the flux within 1 hour and then drop down. So please be note that this is the halfly hour flux measurement instrument compared to the other daily based flux measurement technique. So when the second day, the sunrise, there's some ambient temperature change and another increase on the flux of the ammonia. Pretty good readout. And we also did some data analysis, and this graph is in the paper we published in AFM in 2021. And this graph on the left shows the concentration during the entire experiment, and also the flux during the entire experiment. So even we measure high-speed concentration, when we smooth it out, they also tells us what's the concentration of the ambient flux, ambient ammonia there. So if you want to know more details, please refer to this paper I showed here. And I want to give a deeper explanation how to do this modified WPL correction. We all know that EC flux measurement, especially for open pass laser-based analyzer, you have to modify the WPL correction compared to this near infrared, the NDIR open pass analyzer. So there are some density correction due to temperature and pressure in the open pass. But for laser-based open pass analyzer, you have also to consider about the spectroscopic correction. So followed by the Lycor company's paper, we actually recalculate the ammonia spectroscopic correction coefficient because Lycor's instrument is the open pass methane instrument. The absorption line for methane is totally different from absorption line for ammonia. So we have to recalculate the coefficient. And yeah, so if you want to follow this procedure, and there are some theoretical derivation and some simulation, and we can discuss later after this talk. And this graph shows spectra and co-spectra of ammonia and the other open pass analyzers, and of course wind speeder, wind emitter. And you can see ammonia is this the pink one, and it follows the Caramel model, and there are some attenuation on high frequency due to this ammonia sticky nature. And how accurate of our analyzer is? This is still a question. Is the flux measurement correct? Luckily, there is another open pass analyzers that can measure ammonia flux in the Netherlands. So we approach and we collaborate with the Institute of TNO. It's a institute in the Netherlands. They have an open pass ammonia analyzer called MiniDOAS. This kind of analyzer is based on the UV absorption spectroscopy, and which can accurately measure the ambient concentration of ammonia. So before HT was invented, they used the gradient method to derive the ammonia flux in the field. So for gradient method, it doesn't need high-speed gas analyzer. It's basically it measures average concentration at 2 different altitudes, and it's a mature technology, low requirement on the gas analyzer speed, and it needs data acquisition method. It's a pretty mature technology, and it also needs some day and night data correction. For eddy covariance, I think most of you are pretty familiar with it. So it only needs 10 Hertz high frequency calculation concentration data at 1 altitude. It's a new generation technology, theoretical superior, and it's already widely used for measuring CO2, water, and other GHG fluxes. But it needs high speed or fast, high precision ammonia analyzer instrument for ammonia flux EC method. So we collaborate with TNO, RIVM, and Wageningen University from the Netherlands. We did some back-to-back comparison using their mini DOAS analyzer with our HT analyzer. So this picture shows the setup of the EC ammonia flux measurement station. They hung this HT analyzer on 3-meter height, and it was done in an echo station which is called Cabal echo station. This is how they set up the mini DOAS. Basically, you have to use 2 mini DOAS analyzer measuring the concentration of ammonia at 2 different heights. One is 2.25 meter, another is pretty close to the ground, 0.776 meter. And the open pass actually it's a single or a single reflection. They use the retro reflectors to reflect the beam back to the analyzer to analyze the ammonia spectrum and then retrieve the concentration of ammonia and different height. When they want to calibrate this analyzer, these 2 analyzers, basically they shoot the beam in cross period. So basically, if you shoot the beam in cross period, they mirror the same space of the ammonia, ambient ammonia. So assuming cross period, these 2 instruments or mini DOAS instruments should have the same reading of the ammonia concentration. During this cross period, they can actually get very accurate ambient ammonia concentration result. So, and based on this, the gradient method, they can get also they can get ammonia flux. This is the top view of this setup, the whole experiment setup. So HT is here, and the open pass mini DOAS shooting just besides the HT station. And this circle shows the wind direction or wind statistics from the 360 degrees around this measurement site. So with the very accurate mini DOAS open pass ammonia analyzer, we do see some temperature-based drift on the concentration measurement of HT 8700. But after temperature correction, they basically read the same concentration. And this temperature drift is mainly lead to the offset of the concentration measurement, not the slope of the concentration measurement. So luckily for eddy covariance measurement, when you do the data processing, you basically smooth you basically doing the smooth averaging, and you subtract the average concentration out, and you only got the high frequency signal change. So basically the offset drift doesn't influence on the flux measurement due to EC measurement technique. So the result is that when the team calculate the ammonia flux based on the AGM or a gradient method, those results are pretty similar to the EC flux measurement based on HT, except during the middle of the day, they are a little bit higher flux of ammonia. And during night, both of the instrument or system observed the position of ammonia. And this paper was published on the atmospheric measurement technology in 2023. If you are interested, you can refer to this paper. So there are some overview of these two instruments in the paper. I just copied the table here. So for field performance, the mini DOAS using gradient method is 100 uptime and 65% of flux measurement time. And as I said, the two analyzer has to cross calibration. So there are 35% of the time is during calibration time. And during calibration time, there's no data you can use for gradient calculation. So 65% flux data available. And for HT using eddy currents, there are 79% uptime. And of course, during because the open path configuration, there's no measurement during rain or dew. And for mini DOAS, it's hands off for 7 weeks during campaign. And typically, there are hardware maintenance, like annual lamp and mirror replacement. And it claims ready for long-term monitoring deployment. And for HT, they are also need some mirror changing. And of course, now we have improved the mirror quality, so we can extend the mirror changing period. And it does need some regular operator interventions, like data downloading and manual cleaning of the mirror, because there are some birds waste on the mirror. It's unpredictable, and it needs substantial mirror degradation. During the experiment, it does need replacement after 5 weeks. But as I said, the mirror quality is improved, and we will have a much better or much longer replacement period. For flexibility in application, for mini DOAS, it's a big machine, and it needs housing to shelter rain, and need air conditioning to maintain the temperature of the room. So basically, the power consumption of this gradient system is around kilowatts, and it needs stable base. It's in case the optical beams walk away, and it needs 10 to 20 meters optical paths. So the footprint or the size to deploy the sensor is pretty large. The application above the tall vegetation is not possible yet. Meanwhile, for HT, it can be powered by battery or solar panel. It only consumes 50 watts. And the size of the instrument is relatively small and mountable. So it can be deployed at remote sites, even above the forest canopy. So third, the performance on the concentration and measurement. So during the operational in Dutch area quality monitoring network, it's traceable to certificate standard within 3% accuracy. So basically, the mini DOAS is on internet. It can traceable the concentration the accuracy of the concentration measurement can be traceable to national standard. But for HT, we do observe some substantial deviation, and it need to correct it due to ambient temperature. And as I said, the correction is only for offset correction. It doesn't influence on the flux calculation. And lastly, the performance on the flux measurements. So they said no good standard available. Instrument compared well with exceptions. The nighttime deposition flux is similar, and mini-DOAs observe higher emission during daytime. And both instrument or system need 100-meter homogeneous, obstacle-free upwind terrain. Both need further work on analysis algorithm. And for mini-DOAs, the footprint needs further study because the wind direction influence on the footprint pretty much. And for HT, the flux may or may not be affected by error in concentration measurement. So in conclusion, an adequate system equipped with a commercial open-pass QCL-based ammonia analyzer was developed to measure the ammonia fluxes from agriculture field with power around 50 watts. The instrument has a sensitivity of around 0.3 ppb and 10 Hz sampling rate with a half-lay hour flux detection limit of around 6 to 7 microgram per square meter per hour. That is 95% confidence level, which is capable to sensitive capturing most ammonia emission and dry deposition fluxes. For comparison, there are 3 listed paper have the example of the emissions from different ecosystems. For 2019, Lee ETL estimate emission from farmland are around this number, and Flesch in 2007 reports livestock emissions around 100 micrograms per square meter per hour. And Pan from IAP in 2018 reports dry deposition rate in China is around 9 to 300 microgram per square meter per hour. So it's pretty sensitive enough for HT instrument to capturing those emission level. And a recent study from the Netherlands found that the HT plus EC method calculate the ammonia fluxes exhibit a similar daily pattern of emission and deposition as those measured by the mini-DOA's UV gradient method. So we hope that this instrument will be a powerful tool for measuring ammonia emissions from all nitrogen fertilization events, urban areas, and dry deposition in areas affected by agriculture activities. So with that, I would like to thank you very much for the listening, and I'm happy to take any questions. Thank you.
All right, thank you, Dr. Lin Wang. That really great presentation from you. So is there any questions from the audience?
And maybe if not, maybe I can just ask one first. So I'm just so that ammonia is mostly from the farmland, right?
Yes, from agriculture, I believe. Yeah.
Okay, so that do you have plan for the methane at until open pass analyzer in the future? So I think maybe methane at until are quite
Yes.
popular choices for the flux.
Yes.
For the flux measurement.
Yes. Yeah, methane is really popular. There are already some analyzer on the market, like a Lycor 7700 open pass methane analyzer, which is very useful to measure EC flux of methane. And also methane is a signature of agriculture activity. So it's, you know that ammonia also produced and used widely in industry. It's a fridge agent, and it's also coming from industry stack emission. But for industry, there is no methane as a signature. Only in agriculture, it contains methane. So methane plus ammonia is a really good combination of detecting or distinguishing agriculture ammonia emissions. This is one of the meaningful signature for methane. And we are actually trying to combine methane measurement with ammonia measurement for this agriculture emission hotspot distinguished. So methane, yeah, it's really useful, and we will present a talk in AGU probably this year
Dr.
about
Wang,
our
yeah, so I think I heard that that our course are planning to ban all those open pass methane analyzer because they consider they are not very accurate, they are not very good. So the ICOs are planning to ban those LICO 17.
Yeah, I heard the news. I heard.
So yeah, so I'm just wondering, are you planning to improve this methane open analyzer? Because now it seems it isn't very reliable, isn't very
Yes,
good.
I think the reason why they are not like they do not like open pass methane is that open pass has more noise, or the sensitivity is not as high as those closed pass methane analyzer. And there are also some methane analyzer with very high accuracy, which was done by closed pass configuration. And methane is not sticky. It's not like ammonia. So closed pass methane analyzer can also do the similar job with higher sensitivity. So this is why the open pass methane is not good compared to closed pass. But if you use middle infrared spectrometer, we can increase the sensitivity first of all to increase the availability of the data for open pass methane measurement. So this is one of the advantages of using middle infrared spectrometer to measure methane. And second, I think there are also some complaint about the modified WPL correction for methane measurement, methane flux measurement, because the spectrum line selected by the 7700 open pass methane, they do being influenced by the temperature density effect a lot. So you have to correct a lot by using near infrared methane open pass gas analyzer. But for mid infrared, you can select another line which is less susceptible or less influenced by the temperature density effect. So you can improve or you can reduce the WPL correction number, and this makes the open pass analyzer more accurate for methane flux measurement. Yeah.
Okay, cool.
Okay, thank you, Dr. Yinong. So there are two questions from the chat box. So
yeah,
first question, yeah, can you check the chat box?
Yeah, I see there are two questions. Are you developing any instrument for measuring N2O? Yes, that's in our plan. And N2O is another reactive nitrogen, and which is very important to co-measurement with ammonia. So yeah, it's on our plan and we have such kind of research progress in the lab, in the company. The second question, what is the primary reason for the quick degradation of the mirror on the HT? Yeah, this is basically an engineering question, and it's an optical engineering issue. For open pass configuration, you have to enhance the hardness of the mirror surface to make it very stable, or make it is immune to any scratch. When you clean the mirror surface, when the dust falling on the mirror surface, yeah, you have to improve the hardness of the mirror surface. So we basically find a coating, a special kind of coating to coat on the mirror. But since this is a very novel technology and very new process to do the coating on this kind of metal surface of the mirror, so the coating quality degraded during time under remote site. So all we have to do is to improve with our supplier together to improve the quality of the coating, and we do have some good results actually. So now we are more confident about the changing time of the mirror. So we are targeting change the mirror once per year instead of changing the mirror during last year's experiment by only 1 or 2 months. Yeah. Is there any experience to test HT in different lands, such as wet land and dry land? How was the number range? I think HT can do this work because we have deployed HT in rice paddies, the white rice paddies. So we do see some signal from ammonia emission and deposition. So white land, I think it's pretty same to the rice paddy.
Okay, thanks, Dr. Wang.
Yeah, thank you.
Is there any question from the audience? If not, I can ask some question for both Dr. Kang and Wang. So, open path analyzer has some disadvantages, like when rainfall occurs. So, what do you think about it? Is that affects the data value a lot for the HET 8700 as well? And similar question to this is, what types of gas analyzer would you recommend for the different types of ecosystems, such as agriculture or forest?
So Dr. Lee, so what's your first question? I'm sorry, I didn't get it.
Yeah, so have you ever tried to measure the ammonia flux under rainfall using the HET 8700?
Rainfall?
Yeah.
No, it's hard. It's not possible because the mirror is exposed to the rain, especially for the lower mirror. It's facing upward, and when there's any raindrops on the mirror, it block the laser beam, so the signal drops to 0, and there's no signal. And we actually add some mirror heating function on beneath the lower mirror to speed up the evaporation of the mirror of the water droplet. After the rain, we hope the signal recover as soon as possible so that we can capturing the ammonia emission just after the rain. And this is pretty interesting period of time. Yeah, we add in this function.
So how long does it take to recover from the rainfall?
It really depends on how much water drop on the mirrors. Yeah.
So for example, for users, when users use HET 8700, they must be experience the different weather situations, and after
Yes.
rainfall, they have to select the data period or something like that, you know. So
yes.
the
So
kinds of suggestions would be very helpful for the users.
yes. So you see, in the Netherlands, they conclude the statistics of the data availability. It's about 80% uptime. So the data availability is around 80% uptime, and I think it really depends on the area that has more rain or less rain. And this is one of the questions. And we are improving the mirror cleaning schemes on the lower mirror. So now we have some gas, compressed gas, to blow away the mirror drop, to blow away the raindrop. And I think with our new scheme, we can recover the mirror and the signal within one hour or 2 hours after the rain, when the rain stops. So that's our target.
Oh, that's cool. Dr. Kang, may I ask you what types of gas analyzer would you recommend for agricultural field or forest?
So I think many flux scientists prefer an enclosed path gas analyzer rather than open path or closed path analyzers, except for evapotranspiration measurement, because the H2O water vapor is sticky, so typically the evapotranspiration measured by enclosed path and closed path are under measure. So
Right, thank you. Is there any questions?
Yeah, now maybe we can wait for the questions from the audience, and if you have any questions, so you can just post in the chat, or you can just unmute to ask. If not, maybe we can just share that Slack channel. Yes. Okay, good.
Okay. So, okay, you can leave your questions in the Slack channel. You can see below the QR code, and you can join our Slack channel here. Please do that and leave your question for the workshop day 1 channel. And all right, tomorrow we on second day of our workshop, we will have the presentations from Dr. Peter Isa from Turn and OG Flux, Australia, and Dr. Yusri Yusuf from University Science Malaysia. They will talk about the data processing and analysis techniques and software. So if you are interested in these topics, please join the workshop tomorrow. Okay, so this is that's it for today's workshop. So if you have any question, just leave your question on in the Slack channel. Sam, do you have anything